Try it again.
Hello? Oh, yeah, much better. So yeah, Kirill Pimenov, Parity Technologies, and now you're building blocks for decentralized applications. It is designed this way to remind you of those boring lectures in your high school or wherever you studied programming, and unfortunately they didn't have overhead projections, so we will have to deal with this. And if you remember your course books, they probably drone computer like this. You have a huge mainframe, you have dumb terminals, they are interacting with a single central computer, and basically everything in your course book teaches you how to build software for those systems. And you know what? Skip like 30 years forward, and you have systems which are looking like this. In the center you have Facebook, and you have all the clients around that. And it looks peculiarly the same, only the screens are easier to draw now. And I believe that this is to a certain extent because all the algorithms in those books, they are very, very, very neatly designed to be working on a single computer, and all the algorithms which are better suitable for the decentralized scenarios, for the multi-node environments and so on, they are not that well taught. They are not in all the course books, and because of that, I believe it will be very beneficial to just have a brief look of what those algorithms can be, what you can do with them, like what features they have. It is not for you to learn and go back home and start implementing them from scratch or something like that. But the next time you will have a problem, you will sort of notice that, oh, I remember it was for CRDTs, this is an easy task. And then you solve something by looking it back in like half a year when you see next problem which can be solved in a decentralized fashion. So yeah, we all know, hello? Yeah. We all know this picture, and we all know how purists are making sure that we don't never mix decentralized and distributed applications. But I believe in the modern world it's not that important because we will have multi-tiered network anyway. Like you have cell phones, you have mobile, you have Internet of Things. They are not equal to the full computers or servers which are running your system. So you have some sort of a hybrid between decentralized and distributed, no matter how much you strive for the truly distributed system. But the important thing that properties of decentralized and distributed systems are much closer together than they are different from centralized systems. And this is why new algorithms are required to properly design systems for those. And what's the difference? Okay, two of them. No global clock. And I really can't stop seeing people coming up with new brilliant ideas of projects, of protocols, and they will just arrange something, the earlier one wins or the last one wins and so on, and then you figure out that, okay, in distributed, in decentralized system, you don't have single true source of clock, so you don't know what is first, what is last, and this is not the straightforward problem to solve, and you need to think about that. But a lot of our reasoning about algorithms, how we taught to reason about algorithms in schools, because maybe of the way we are taught using imperative languages, they all have that implicit notion of, okay, this is the flow of time, this is the flow of operations, they are going one after another. And it is really hard to grasp that, but it is possible. And the second thing is really malfunctioning or malicious nodes. You cannot be the gatekeeper. As soon as you introduce a new system, the single gatekeeper which separates good nodes from bad nodes, allowed nodes from disallowed nodes, you're back in the centralized world. You still have a centralized system which tells all other nodes the rules of the game. And the aim is not to have that. And because of that, yeah, the system should survive having malicious nodes. The system should survive having nodes which are malfunctioning or have really laggy internet or something like that. And you just need to design for that, and you need to put an additional effort, and you need to put an additional algorithm just to solve that. And here we have a couple of important words which are basically names for solutions for those problems. Linearizability. Linearizability. Yeah, this is basically our ability to put some order into the events which are happening in the system. And when we will talk about a couple of particular algorithms, we will see how we can achieve that property. And another, like, I hope everyone heard about that. It's Byzantine fault tolerance. And basically, it is ability of system to still function if some nodes are not only malfunctioning, but they are actively malicious, they're trying to trick you into doing something wrong, they're trying to ruin your system. If it can survive that, then yeah, it has that BFT property. So let's go to the toolkit. Let's see. Asymmetric encryption. Everyone heard about that, but it is crucial in the decentralized systems, because if we are talking about system with no gatekeeper, the asymmetric encryption is the only way for you to have identity and to maintain authenticity of your messages. Because there is no, like, you cannot log in with Facebook. You cannot delegate to Facebook being a gatekeeper, verifying that you are you and no one is pretending to be you to gain something in the system. So asymmetric encryption, having a private key, is your identity. And you can use it both for encryption. So basically when someone sends a confidential message to you, then can use asymmetric encryption just to encrypt. And you will be the only one, practically speaking, who will be able to read that message. And at the same time, when you are sending messages, you can verify authenticity of your messages. So no other node in the system can simulate, can just pretend that the message is coming from you if you haven't been involved with your private key signing the message. It is important to remind that you still should use symmetric ciphers for everything you can. And you should use asymmetric encryption only in the really, just to sign the hash instead of signing the whole payload, or just establish the session key and for the symmetric encryption, and then do symmetric encryption during the whole communication. Because otherwise, you will end up like 3 or 4 orders of magnitude slower than you can be with symmetric encryption. And generally, that is nowadays the borderline between practically usable systems and just theoretically interesting. Unfortunately, yeah, that's true. So it requires some additional thinking, but in the end, the baseline is when you need to establish something to your node, use asymmetric encryption, and then try to fall back to the symmetric system as soon as all the members, all the endpoints in your node communication are established. You can just communicate about the shared key, and there are special things which are called ratchets, which help you keep secure that communication over long periods of time. Yeah, and speaking of symmetric ciphers, the Chacha 20 and Poly 1305 is the best thing you can get in 2018. Use that instead of IS if you can, because you will have benefit of being fast on the machines which don't have IS as a chip in the Intel CPU. Content-based addressing. Really, not very much can be said here, especially for people who've seen Git at least once in their life. But yeah, the idea is that creating names for things is hard. We all know the programmer's jokes about creating names for things. And in the systems which are expected to survive a long time and survive across cultures and survive across like being understood by both computers and programmers, making hash of a content the ultimate address of a system, of a content in the system, is really the maybe most natural way to store it and to retrieve it and to address it in general. So if you're familiar with magnet links in BitTorrent, that's how BitTorrent using content addressing to determine the content you want to get. If you've ever seen the IPFS address, that's it. If you've seen the git commit is basically the hash of all the commit changes in these commits. It is uniquely identifying the particular commit, and it's uniquely identifying the particular content of this commit. And yeah, if you add signatures to that, you get something which is also verifiable. And those are more elaborate, like probably algorithms we want to talk about, just not just call them aloud. And peer and resource discovery is basically you want to work in a system where just some undefined, not permissioned amount of peers communicate and play nice together, or not very nice, to reach some goal, to participate in some network. And obviously we can do better than just having centralized entry points. Like, it's inevitable probably to have a boot node, the nodes you use for first connect to the network, which are maintained by someone and which have predefined addresses. But after that, there are nice algorithms you can use to find other nodes. And after you bootstrap, after you light the fire of your network for the first time for the client, it will keep on connecting to the network without any centralized authority, which is a nice property. The first rather obvious thing to do is just scan your local network for the peers. And it is surprisingly how frequently that is beneficial to have been able to just enumerate in the same Wi-Fi, in the same enterprise network, in the same home network, other peers which have the same system. Because that will give you the closest to you, the fastest, and probably the most responsive clients you can ever find. And there are a couple of existing tools you can use to just find all the clients in the local network. And notable algorithms here are MDNS, which is the one behind Apple Bonjour, for example. And another is SSDP, Simple Service Discovery Protocol, and it's part of UPnP specification. They differ a little bit. One is push-based and another is pull-based. Basically, one is teaching, hello, I'm providing this service. Everyone who is interested, please note that down. And another is just querying the network. Hello, anyone has the service X because I'm very interested in that. But generally, they are sort of the same. They are widely supported in the routers you have in any network. And basically, this is just sending one UDP packet in the network, which will be retransmitted to all the nodes in the network. And then they will figure out how to respond or how to react on the info you just multicasted to them. Second thing, which is really widely deployed and which is also very interesting because it is also resource discovery, not only peer discovery. Basically, you can use it to discover any information which can be reasonably hashed to the fixed length hashes, not necessarily node keys or something. And those are distributed hash tables. Nowadays, it's Kademlia, but there was a huge primordial soup of different hash tables. And if you read Wikipedia about that, maybe you can find some hash table which better suits your needs, better suits your usage patterns. But generally, it works like this. You have your identifier of the content you want to find, be that location of the node in the network, like you have its public key, which is identity, and now you need to find the IP address of that node. Or you have a content identifier, and you need to find a list of nodes which have that content so they can share it with you or something. And you basically figure out the mapping between those hashes of content and coordinates of the nodes you know, and you figure out the way, what is the closest. Typically, people just hash the IP address of other party you're communicating with, and you have two hashes, and then they use so-called XOR metric. Basically, they count amount of different bits in both binary numbers, and where that difference, the number of different bits is shorter, that is the closest neighbor. And then you go and you ask the same question to that closest neighbor, and closest neighbor does the same. And there is a proof, it can be proven, that in logarithmic amount of steps, like if you have n nodes in the log of n steps, you will find the node which is actually what you're looking for. And then you propagate the answer back. So basically, it's a way of asking neighbors to ask neighbors, and it's a way to structure the question the way that it gets closer and closer to the node with an answer with every pass of the message down. Yeah, and the third one is less known, rather interesting recent development called gossiping protocols. I heard for a long time, but it feels like recently certain problems with them have been solved with Brahms protocol. And what is gossiping? It is a little bit like questions in DHT, but it's mostly for just, oh, I have those nodes around me. Maybe I can just tell about them to the other nodes I have. This is basically how gossips work, like in the human world. Like, I know something about something, I can tell it to a couple of trusted friends of mine, and then, oh, everyone knows about that. So problems with gossiping is malicious clients. We talk that they have a problem in our networks. And the problem is that your peers cannot be very good to you and then can feed you with disinformation. And the problem is that when you ask your peers for the gossips, you're probably not getting the uniform, like you're not getting the perfectly random over the whole network sampling of the results. Like, I want 20 more nodes in my network, and they will feed you with disinformation or something, and the only one truthful node you have connected to won't be able to fight back to that false gossiping. And Bram's protocol is nice that it is designed the way this is not a problem. It is sampling the network uniformly, so when you ask Brahms for additional nodes, for additional peers, you will get the random sampling of all the network, even if you don't know like what is the whole network is, and still is pretty effective, like you don't need to download the whole table of the peers, which will be prohibitively expensive. Another overlooked class of algorithms is conflict-free replication data types, CRDTs. And there are operational transformations, OTs, which are they're logically equivalent. And OTs are harder to implement. They have more moving parts. So I will be mostly focusing on CRDTs, but probably the properties you will observe can be used by both of those algorithms. And CRDT, like, you all know Git, and you all know what is a merge conflict. Basically, there are two branches in the history of changes which cannot be trivially merged together. And if you just say that you allow random operations on your data structure, then conflicts can arise. But CRDTs are the way of us to express data structures in a more complex way, but in a way that conflicts never arise, so the operation of merging things back together, that operation is always defined, and that operation is always valid, like it gets you the result you actually want to see. Let's see a couple of easy examples how they work. They're actually not very complicated, and I wonder why they're not very well known. And this is G counter, or growth counter, counter which only grows all the time. And you can see we start with node A. And to count something, node A just puts 1 into that, like, okay. Yeah. So node A puts 1 into the register with a node. We already have asymmetric encryption, so we can make those messages to be not falsifiable. So we trust that it's not actually node A which puts that value into that register. And then the structure just propagates node B, which then loses connection to the node A, and it increases its counter a couple of times. Yeah, I'm bad with math, sorry. This should be 1. So node B registers the event, and it writes it in the counter with section B, and at the same time, node A registers the event, and it registers it with a counter A. So this is increment for the node A, and this is, like, given that this will be the number 1, it will be increment for the node B. Both of them now have a global counter of 2, like 2 events have been encountered. But when we merge them back, we basically take the largest of every register we encounter, and this is our merge operation, and it is defined all the time. We can, like, compare numbers in every register, and then our global counter state is just sum of all the values in all the registers, which is free. And it is valid because, yeah, we incremented it once here, we incremented it once here, and we incremented it once here. So basically we counted 3 separate events, and our merge operation clearly pointed us to the valid counter number. This is rather simple, but the thing is that you can, from really simple counters, you can have, for example, positive-negative counter, which can not only grow, but it can go downwards. And for that, you just record the pair of 2 numbers. And if you started with a state of counter plus 2, then you decrement in A. So basically, you decrement the second number in the A register, and B is initializes it with 0 and also decrements the second value. And then merge once again is defined because you can just take the larger number in every section, and will be your PN counter merging. And you can see this is one decrement, this is two decrements, and basically after the merge, we have the valid value of 0. This is rather boring, but this is important because this shows you how you can nest together the CRDTs from very basic ones to express any data structure you can, and this is actually provable, and there are like implementations of arbitrary JSON data types, which you can do with CRDTs, or you can just use them as a library. And yes, they are a little bit harder to work with than just basic number 0, which you are passing around, but they have this nice property of working in systems where the nodes can get disjoint and join together. And you have all your basic primitives from which you can build. There are counters, there are registers, there are sets, graphs, and sequences. Basically, everything you can express with that. You can express text as sequences of letters. You can, more complicated data types are basically the graphs with values in the nodes. And this is really nice thing to have in your distributed systems because it gives you ability to edit something offline and then get online and get the valid results in the end. Consensus protocols, that's basically the bread and butter of the modern blockchain revolution. And there are like rather boring requirements, which basically nodes need to reach consensus. They need to reach to some value of all the possible values. They need to elect a leader, or they need to figure out if something is a valid transaction. And there are just boring technical terms of what requirements are, but in the layman terms. Termination means that on each node, computation should stop and it should come to some conclusion. Rather a simple thing. Infinite loops are not allowed in consensus protocols because, yeah, then you will post something which will end up in an infinite loop on the nodes and the network is falling apart. All correct integrity, all correct processes come to the same conclusion from the same inputs. Yeah, like there is no randomness in that. Otherwise, it might or might not be the same consensus from time to time, and this is not desired property. Validity, like if one of the values proposed by, like one of the correct nodes will propose the value which will win in the end. So it is one of the valid values which will win, even if the nodes don't have the full information from the start. And yeah, all nodes decide on the same winner. 3 and 4 are a little bit theoretically hard to distinguish. Like first one is talking about where the actual valid result comes from, and the fourth one is talking about how nodes are all together decide that, yeah, this is the valid number. But practically speaking, for us, it is only important for linearizability. You remember that word I cannot pronounce properly. And basically, to linearize something, we can use consensus protocols to elect the leader, elect the something which will give us the linear time for certain shard of the network existence. And agreement on leaders is usually what we need. Leaders definitely should be rotated to prevent malicious behavior, but yeah, this is a blockchain. We just lead the something which is a block author on some sort of a consensus protocol. And two types of consensus protocols. Lamport is what we know. Classical protocols, they are typically permissioned, synchronous, but they have absolute finality. And if you've seen multi-master database anywhere, there is either Raft or Paxos. They're both based on the original works of Lamport and maybe Liskov. Nakamoto is the novel consensus. Yeah, we all hear about because of this. And they are permissionless. Basically, any node can participate. They are asynchronous, but for that you pay that finality is only probabilistic in the general sense. We can simplify that a little bit, but generally, yeah, Nakamoto consensus is probabilistic, so you're never sure that, yeah, the block will be discarded because longer chain popped up from out of the blue. And there are some novel approaches which I'm not yet sure about, like the avalanche sounds like an exciting protocol. It is widely discussed out there. And for example, Emin Serrer from Cornell University is pretty high opinion of it. And Vlad Zamfir, for example, is pretty low opinion. Read it up. It is really wonderful stuff, and probably it's somewhere in between classical and the Nakamoto consensus. So let's play with those bricks. Let's combine them and see how we can build the systems we all know from those building blocks instead of centralized servers where everything is settled in the final. And file sharing network like torrents or IPFS. Yeah, we need content-based addressing. I already mentioned that. We need peer discovery. We need to know what nodes we're talking to. And we need content discovery. Basically, with just DHTs and content-based addressing based on hash, we are good to go. Encrypted overlay networks. Those are rather important, like the Tor and IPFS projects you probably heard of, and projects like CJDNS or Yggdrasil you probably haven't. But they basically allow nodes to communicate agnostic of the actual fabric of internet, these avoiding the censorship and these avoiding the way the network's structured nowadays. So you will be able to upgrade the network, but the Tor will work even on top of some other protocols. And CJDNS works for mesh networks as well as the traditional internet. So no provider is required to be a part of the net, and you still will be a part of the connected of it. And yeah, you just need to find the nodes, and you need to be able to identify as a node. So you have asymmetric encryption, and you have peer discovery, and everything else is just a lot of really hard programming work. Distributed ledgers, they're not like blockchains for those who are not about very technically correct descriptions. And yeah, asymmetric encryption, hello? Yeah, asymmetric encryption to identify nodes, peer discovery, and consensus protocol. Collaborative editor, something like Google Docs or HackMD or real-time board. Yeah, you just need asymmetric encryption again because in your distributed systems there are no other node identities. And you need CRDTs basically express your document, whatever it is, in the conflict-free fashion. And you have a peer discovery to know with what nodes you want to communicate with. And it's like social network. Hello? Yeah, all of them. Social network, everything we talk about, mix and match, and you have something decent like a blogosphere of 90s. Probably it will require some additional protocols and additional tools and a lot of work to make it on par with Web 2.0 social networks we all know and love, hate relationships, whatever we have with them. But it is possible. And yeah, just a quick notion of everything else you might want to see. Ad hoc routing protocols, your nodes are not necessarily being able to talk directly. This is assumption of the internet, and it is false, like people are behind NAT, or some clients are inside of the browsers where only WebRTC is present. So ad hoc routing is a way you can route effectively in this network. Yeah. So verifiable delay functions figure out the function which can be easily checked, but it cannot be predicted, so it takes some delay for nodes to compute it. Distributed secret generation and threshold signatures, really exciting thing. You can generate the secrets among nodes where not single node knows the secret in the whole, and you can use it in crypto, either to encrypt or decrypt messages. Zero knowledge proofs, variation of the last previous one. You can prove something to the nodes without disclosing the actual thing you're proving. Multi-party cryptographic ratchets are the way you just upgrade your symmetric key all the time to give additional cryptographic properties to your communication. So basically when your key is leaking, your messages are not leaking, even if some third party knows the keys. And homomorphic encryption is a nice new thing which allows you to transparently operate on the data you don't know about. Basically, it's programs on encrypted data which give you encrypted result. Yeah, many more. Keep on reading. Lots of interesting developments in the field. Thank you.